the last class, we were discussing the growth of perturbations in an expanding universe, and we have been treating the constituents of the universe, the matter that makes up the universe, as a continuum which can be described by the fluid equations. So, we had written down the fluid equations and then transformed the whole thing to an accelerating, to an expanding coordinate system. So, we have shifted over to a coordinate system x which is expanding, and the fluid velocity was also broken up into two parts. One part arises because, so the velocity of the fluid is actually now, if the fluid is at rest with respect to the expanding coordinates, then it will have a velocity a dot x. Any deviation, any excess velocity with respect to that is v, and we had then written down the equations in terms of v. In the cosmological context, we have gone to a coordinate system that is expanding with the homogeneous isotropic background cosmological model, and v is the deviation from the predictions of the Hubble law of expansion, and this is what is referred to as peculiar velocity. So, we had written down the equations, the fluid equations, in terms of this x and this v, and then having done that, we first worked out the equations governing the background model where the universe is homogeneous and isotropic. In such a situation, there are no peculiar velocities, the density is the same everywhere. It is just a function of time. And we recovered the same equations which we had worked out earlier for the homogeneous and isotropic cosmological model. Having done that, now we put a small perturbations on this background model. So, we have this rho which is the background density, and we have these perturbations which are fluctuations in the density. And we quantified these fluctuations in terms of the density contrast delta rho, the fluctuation in the density divided by the mean density, and this was denoted by delta. And this density contrast we had assumed was much smaller, of the order of some very small number epsilon. The peculiar velocities were also assumed to be of order epsilon. Under this assumption, we could drop all the higher or nonlinear terms. So, the fluid equations are nonlinear, and it is not possible to solve them without making certain assumptions. So, you can solve them if you have some symmetry like spherical, etc., but we are dealing with a homogeneous and isotropic universe with some fluctuations in it. So, there is no such symmetry, and it is, so what we have done is we have assumed that these fluctuations are extremely small compared to the mean density. Under this assumption, the mass continuity equation gives us this. This is the mass continuity equation. The Euler equation can be written in this form: del V del T plus A dot by A V is equal to minus grad phi by A, where phi is a new potential that we have introduced. The term arising from the pressure gradient was dropped because this term is important only on small scales, and the role of this term is to prevent the growth of perturbations. It makes them oscillate. We are interested in the growing perturbations, in fluctuations which, if you introduce in a background universe, will grow, and we have seen that the pressure gradient term effectively prevents the growth of perturbations on length scales smaller than the Jeans length scale. So, we are not interested in this, we are interested in length scales larger than the Jeans length scale, and we have dropped the pressure gradient term. So, we have, this is the Euler equation governing the peculiar velocity. We have introduced a new potential phi, which is the difference between the old potential and some other quantity. And we also worked out what this phi is. So, this phi satisfies this equation. So, the Laplacian of phi is 4 pi g rho bar a square into delta. So, the original Euler equation had the gravitational potential due to the entire matter distribution. Now, we have the model that we have an infinite universe. So there is an infinite matter distribution, and in Newtonian gravity we really don't know how to handle this. So by going to an accelerated coordinate system, to an expanding coordinate system, the potential due to this background matter distribution, the uniform background matter distribution, actually cancels out from this, and the peculiar velocities are governed, the evolution of the peculiar velocities are governed by the gravitational potential phi, which is produced only by the density perturbations. The mean density does not contribute to this. So at the end of the day, we have three equations. Let me write them down for you again. So in linear perturbation theory, in an expanding universe, we have three equations. The first equation, the continuity equation, then we have the Euler equation, the linearized Euler equation, and we have the Poisson equation, so we have these three equations which we would like to solve and determine how these density fluctuations grow. Now to connect this with what we have already done, if A is a constant, suppose A were a constant equal to 1, then this term would be 1, this term would drop out, I would have 1 here and 1 here. And if I were to then simultaneously solve all of these equations, I would recover the solution which is there on length scales larger than the, much larger than the Jeans length scale. So if there is no expansion, let me remind you, if A is constant, is a constant value 1, then we would recover the solution which we have already worked out. I would have two parts to it. One part would be okay, the time, let me just tell you the time dependence, there will be two parts to it. So the time dependence would be e to the power square root of 4 pi g rho bar t, and there would be another time dependence e to the power minus square root of 4 pi g rho bar t, and there would be some spatial part also. So this is in the absence of expansion. Now the main thing here is we would like to now see what happens, do perturbations still grow, and how do they grow in an expanding universe? That is the main thing. Okay. So how does the expansion come in? The expansion comes in through the scale factor. So now notice we have the scale factor coming here, A dot by A coming here, scale factor here and scale factor here. So the whole thing is now dependent on the expansion of the universe. So A of t is a function which has to be determined by solving the background cosmological model, and the solution explicitly depends on the form of A of t that you choose. Okay, so it depends on the background model. Let me, so how do we proceed to solve these equations? We proceed in exactly the same way as we had done earlier. What you do is you first take divergence of this equation. We had done the same thing earlier, right? So take the divergence of this equation. Let us take the divergence of this equation, the divergence of this equation, and in the divergence of this equation we will replace this, and we will replace this. So the divergence of V is A into del this partial derivative of delta with respect to time. Okay, so let us with the negative sign. So let us write down this first term first. So the first term, what it gives us is del by del t minus A into that is the first term. The second term now is plus this is equal to, that is the second term, minus del square phi by A. Del square phi, if I take divergence of this, is 4 pi g rho bar A square delta. So this becomes equal to one A cancels out. So let us expand this. The negative, the minus sign can be dropped throughout, and if I expand this, what I get is that this, okay, let me write it out. I will have A into del square then I will have plus A dot by A, sorry, A dot into, that is the second term. This will give me plus A dot, same thing as this previous term. This is equal to 4 pi g rho bar A delta. So finally we have this equation that is the equation governing the growth of density fluctuations in an expanding universe. The density contrast follows this equation. Now the question is, how do we solve this equation? The first thing that you can do is that we can take a trial solution delta x t is d of t into delta x. Now note that there is again some, the convention here is not the best possible convention, but this is what we are going to use. So the density contrast as a function of x and t I have written as some function of time and some function of x. The function of x is again the same as delta, but it should be clear from the number of arguments that this function is different from this. Okay, so this is a different function. So this function of x and t we are decomposing into a function of time and a function of space. And if I put this here, so I have done a separation of variables. If I put this here, then the delta x, the spatial part cancels out throughout, and we are led to an ordinary differential equation So what we see is that whatever perturbation you put, okay, so okay, we can, if we decompose the density fluctuations into one function of x of position and a function of time, then the whole thing reduces to just solving this ordinary differential equation. Now, the solution obviously will depend on the background cosmological model, because you have this a or a dot by a, the Hubble parameter, coming in over here. Right. So, the evolution of the Hubble parameter is different for different cosmological models, and the solution, the way the perturbations grow, will also be different for different cosmological models. Okay, so let us now work out one case explicitly first. Let us take the cosmological model where omega matter is equal to 1, there is nothing else. This is the familiar Einstein de Sitter cosmological model, and we have worked out this cosmological model in some detail. Okay, so let us work out this cosmological model thoroughly. So, if omega matter is equal to 1, there is only matter, nothing else in the universe. Then we know that let us first write down the equation governing the scale factor. A double dot is equal to minus 4/3 pi g rho bar A. There is no cosmological constant. So, this the matter, it is the matter which contributes completely to the A double dot. We also know the solution. Recollect what was the solution. The solution was A of t. The solution was A of t is equal to t by t naught to the power of. So, in the Einstein de Sitter model, if you remember, the solution was t to the power 2/3, right. So, this is t to the power 2/3. Okay. So, now we want to use these here. So, how much is A dot by A? We have also worked out A dot by A here. A dot by A, if I differentiate this, I will get 2/3, and then if I divide by A again, I will get 1 by t. Okay. So, this was equal to 2 by 3 t. Okay. Now, we also need this 4 pi g rho bar, right. Now, you can get 4 pi g rho bar from this. 4 pi g rho bar, the mean density, is equal to minus 1/3 A double dot by A, right. No, it's equal to 3, sorry. 4 pi g rho bar is equal to minus 3 A double dot by A. Okay. So, we want to calculate A double dot by A. Let me do it somewhere else. So, A of t is equal to C t to the power 2/3, that is what we have seen. So, A dot is 2/3 C t to the power minus 1/3. A double dot is equal to 2/3 minus 1/3 C t to the power minus 4 by 3, and A double dot by A. So, we are interested in calculating minus 3 A double dot by A. This will be equal to, so I multiply with this with minus 3. So, this is going to be multiplying it with minus 3 means this term is gone. So, I am going to have this is equal to 2/3 C t to the power minus 4/3 divided by t to the power 2/3. So, I am going to have 1 by t square, right. A double dot by A is 1 by t square, that is with some factor, we just calculated the factor, it is 2/3. This also is 2/3. Okay. So, so we can now substitute these in the differential equation that we wish to solve. This is the differential equation that we wish to solve. So let us substitute these in this differential equation. So the equation that we wish to solve is d double dot, putting in these factors. So A dot by A is 2/3 t, so this becomes plus 4 by 3 1 by time d dot is equal to 2 by 3 d. D is a function of time, okay, by t square. Fine. So that's the equation that we need to solve. Now, this is a homogeneous equation. So the solution we know is of the form some constant, let us say b, t to the power n. So the solution is of this form, we know this for such homogeneous equations. So if you plug this in here, what you get is n, if I differentiate it twice, I will get n into n minus 1 into b t to the power n minus 2, that is the first term. The second term is plus 4/3. I have to differentiate it once. If I differentiate it once, I will get n, and then I divide by t, so I will get again b t to the power n minus 2, and this is equal to 3 by 2. I have to divide this by t square, so I will have b t to the power n minus 2. So these b t to the power n minus 2 cancel out throughout, and I am left with this relation for n. So it cannot be any arbitrary n which gives a solution, it is a particular value of n which gives me solution. So I have n into n minus 1, let me take the 3 over here, plus 4n is equal to, this will be 2 by 3, sorry, not 2 by, so this will be equal to 2. So we want solutions for this quadratic equation 3n square. 3n square, now I have minus 3n plus 4n, so I have 3n square plus n minus 2 is equal to 0. So we want essentially solutions for this quadratic equation 3n square. So how can we factorize this? Let us see. So 3n minus 2 n plus 1 is equal to 0. Does it do the job? 3n square plus 3n minus, right. Also this is the equation. This equation can be factorized into this. So we now know the solution. There are two solutions. The two solutions are n is equal to 3 by 2. That is the first solution. The second solution is n is equal to minus 1. So we have the two solutions. So we see that there are two possible solutions. One solution is d of t is proportional to t to the power, sorry, 2 by 3, not 3 by 2, t to the power 2/3, and the other solution is d of t is proportional to 1 by t. Okay, so we have worked out two solutions. So we had a second order differential, ordinary differential equation to start with, and it is obvious that there are going to be two solutions. So, we have worked out these two solutions for a particular model where the omega matter Einstein de Sitter universe, okay, where omega matter is 1. Now, let us now interpret these two solutions. So, if I have a density perturbation which is, let me first consider this. So, okay, you see the two solutions, there is one that grows with time and the other which decays with time. This is exactly analogous to the situation where the expansion is not there. The only difference being that when the expansion is not there, you have an exponential growth. Now, because of the expansion, the growth is somewhat slower. It is a power law in this case. Okay, so the growth, you find the same features that you have one growing mode of perturbation. So, in the absence of expansion, you have a part of the perturbation that grows exponentially like this, a part of the perturbation that decays exponentially like this. And I had told you that if you put an arbitrary perturbation, it will be a combination of this and this. A part of it is going to grow, a part of it is going to decay away. The same thing happens if I do the analysis in an expanding universe. If I put an arbitrary perturbation, a part of it grows. It does not grow exponentially, it grows slower. It grows as a power law in this case. Okay. A part of it decays away as 1 by t. The decay is also not as slow, as fast as it was when there is no expansion, but the main feature remains the same. There are two modes of evolution of the perturbation. This is called the growing mode. So, I am going to denote this by d plus. This is the growing mode. This is the growing mode of density perturbations. This is the decaying mode, d minus. And for this cosmological model, the growing mode behaves in exactly the same way as the scale factor. The scale factor grows as t to the power 2/3, the universe expands as t to the power 2/3, and linear perturbations grow in exactly the same way. So, in this particular cosmological Einstein de Sitter cosmological model, the growing mode d plus A is proportional to A itself. Okay. We have two modes of the perturbations or growth of perturbations, the growing mode and the decaying mode. Now, so if I have some arbitrary perturbation at some initial time, so let me write down, I have some arbitrary perturbation delta x t. This can be decomposed into one part d plus t delta plus x. This is the growing part, this is the part of the perturbation that is going to grow, and there is a decaying part . So, if we start studying the evolution of these perturbations at some initial time t, then at some later time this part, the decaying part, is going to be much smaller compared to this, and by and large we are going to be interested only in this part. And sometimes I will not even show the subscript plus. It shall be implied that we are looking at only the growing mode of perturbations. In general, it is a second order differential equation, so there will be two solutions, there will also be a decaying part, but the decaying part decays away very rapidly, and it is of not much importance in the formation of large scale structures. Okay, so it is the growing part that gives rise to large scale structures. So what we see is that in a cosmological model with omega matter equal to 1, matter dominated cosmological model, perturbations grow in exactly the same way in which the scale factor also evolves. Okay. So, this is the crux of the whole analysis. So, let me draw it pictorially and explain it to you. So, we are interested only in only the growing mode. We shall not look at the decaying mode at all. So, if this is what the perturbation delta, the density contrast delta as a function of x looks like at some initial time Ti, T1 let us say, at some later time what would have happened is that the spatial dependence would be exactly the same. The delta x, the spatial part will be exactly the same. The only thing that would have happened at a later time is that this function here would have grown. Okay, and it will look the same perturbation, same density fluctuations will look like this. The amplitude would have become larger. This is at some time T2. And this linear evolution that we have discussed, where the spatial form does not change, only the amplitude keeps on increasing with time, this is valid provided this density fluctuation is extremely small. Once the density fluctuation, once this density contrast becomes of order unity, this whole thing breaks down. Okay, so this analysis breaks down when the density contrast is of order unity. Okay. On the negative side, this cannot cross -1. But on the positive side, it can be arbitrarily large. So, at late times, let me just roughly sketch for you what this will look like. So, this is my density contrast, this is the value -1. So, at late times, I start with a density fluctuation that looks like this. Now, it can reach a minimum value 1, but it can reach, there is no limit to the positive value, but the total average of delta should be 0, because this is a fluctuation from the mean. The mean value has to be rho bar. So, the density fluctuation contrast delta, its average has to be 0. So, what will happen is that a large part will become empty and there will be very high density regions okay, like this. Okay, it will become something like this. This cannot cross, it may not be exactly -1. So, there will be very large regions which are underdense, but not very severely underdense. It cannot be, the density contrast cannot fall below 1. So, which have nearly 0 density, and there will be small regions where the density is very high, like our galaxies, clusters of galaxies, etc. Okay. Let us estimate, or okay, I give it to you as an exercise. Let me do a few examples and give you an exercise. First, by what factor, let us estimate by what factor the density contrast increases between z equal to 10 or z equal to 9 and z equal to 0. In a omega matter equal to 1 cosmological model. Okay. So, by what contrast, by what factor does it increase? This is very easy to estimate. What is the value of Z A here? So, this is, let us say, the initial value I, and this is the final value F. So, A initial, how much is this? A is 1 by 1 plus Z initial. So, this is 0.1. So, the D initial, the growing mode, is proportional to A. So, let us say that this is also equal to 0.1. There could be a factor, it does not matter. Okay. A final is 1. So the D final is also 1. Okay, they could be constant, but it will multiply both of them, does it matter? Okay, this could be into B, this also into B, some constant. Now we want to calculate by what factor the density fluctuations grow. So dF by D initial, this is equal to 10. Okay, so straight away we see that if linear theory on scales where the linear theory is valid, the density fluctuations were 10 times smaller at a redshift of 9. Okay, density fluctuations were 10 times smaller at a redshift of 9. Okay, so as a function of redshift, it is very easy to work out how density fluctuations will grow. This was a very simple exercise. Now, so if I plot in this particular model, if I plot the growing mode D as a function of the scale factor, it is a straight line with slope 1. If I plot log D versus log A, or even in a log, let us say log then it is a straight line with slope 1, and this is valid in the regime when the universe is matter dominated, and that is totally decided by the background cosmological model. And we have worked out at what redshift the universe becomes matter dominated. That is at a redshift of around 10,000, 10 to the power 4. So the scale factor log A, log base 10, this growth is going to be valid at values of the scale factor which are larger than the 10 to the power, or this should be minus 4. Okay, so or where A is greater than 10 to the power minus 4. Right, that is when the universe becomes matter dominated. Before that it was radiation dominated. The behavior was different. So once the universe becomes matter dominated, the growing mode scales proportional to A. So if I plot a log D log A graph, it will be just like this. And the universe is matter, till what redshift does the universe remain matter dominated? The universe remains matter dominated all the way till a redshift of order unity, where it becomes cosmological constant dominated. So roughly till 0, so that is A of the order 1, somewhere over here very close to our present, the universe becomes cosmological constant dominated. So this expansion, this linear expansion is valid for a large part of the evolution of the history of the universe. Okay, redshift 10,000 all the way up to redshift 10,000. Now you can only see objects up to a redshift of few redshift, and you can see the CMBR all the way up to redshift of 1000. Okay, so for all of this, this model holds, this growth of perturbation holds. Okay, it is only in the nearby universe where the universe has become cosmological constant dominated that it breaks down, and in the radiation dominated era which you can't see directly. Otherwise this gives you a good picture of the growth of perturbations. Okay. Now we want, the next thing that we would like to do is we would like to now work out the general relation. We have worked out how in a particular cosmological model the perturbations grow. Now next what we would like to do is we would like to obtain solutions for the growth of perturbations in any arbitrary cosmological model. Now, the general features you can see straight away. Again, there will be two solutions, right? That much we know, because it's a second order differential equation. And what is going to change is this A dot by A from cosmological model to cosmological model. Okay, so now question is, you have to put in this function of time and solve this equation. Okay, let me discuss a particular method for solving this, which will give you a solution. So the basic idea over there is as follows. Now we have, you see, the equations, the main difficulty in solving this, okay, the equations, the basic idea is as follows. We know how to precisely solve the background cosmological models. Okay. Now suppose I had a spherical region. The way we arrived at the background cosmological model was by considering a spherical mass distribution, a part of the universe which was a spherical mass distribution. So we had arrived at the background cosmological model by considering a part of the universe which was a spherical mass distribution and writing down the equation for a test particle over here. That is how we had arrived at the equation for the background cosmological model. Now suppose I have a spherical overdensity in a background in some background cosmological model. Suppose I had a spherical overdensity in a background cosmological model. The equation governing this spherical overdense region would be, or underdense region, would be exactly the same as the equation governing a cosmological model, right? So what we can do in principle is then that, and okay, that is the first thing. So the equation governing a spherical overdense region is exactly the same as the equation governing a background cosmological model. The only difference is that the initial condition, you see, the equation governing it would be the same. Now the initial conditions are going to be different. There are two possibilities: either the initial density was different, at some time the density is different, or the time instant when I start the whole model is different. Okay, so think of it like this. I have a particular cosmological model and I have another cosmological model which has a different density. Say this is a cosmological model with a different density. And the deviation between these two I can think of as a perturbation. Okay. So why is this picture correct? It is correct because we have seen that the growth of perturbations in the linear theory does not depend on the spatial dependence. So if I choose that delta x to be a spherical form, then the equation governing a spherical overdense region would be the same as the cosmological equation governing a cosmological model. Okay. So the deviation between two cosmological models can be used to study the growth of perturbation. So if I think of this as my background model and this is a spherical overdense region, then the deviation between these two is the growth of perturbations in this background model. That is the basic idea. Okay. Now there are certain physical insights which you can gain from this picture. Suppose I have my background cosmological model is omega matter equal to 1. Just the critical cosmological model. In this cosmological model, if I increase the density slightly, then it is going to be a model that is going to collapse. E becomes negative. This is just the critical model. If I decrease the density slightly, it is a model that is going to expand forever. Okay, so in this cosmological model, overdense regions always collapse. It is going to grow. The perturbation is going to grow and finally, right? Underdense regions are going to become more underdense. But suppose I had a different situation where my background cosmological model is omega matter less than 1. This model is never going to contract and collapse. Now I consider a dense perturbation in this. So this is going to give me something like this. There is no guarantee that this is going to actually grow, this perturbation, because this again is another, this could be another omega matter less than 1 cosmological model. Okay. So this is, so perturbations will grow definitely if I can, if they are like this. Okay. Now let me make this first, let me first quantify, put and prove to you that what I am saying is correct. Okay. So we consider a background cosmological model. Okay. And so there is a background cosmological model, rho bar, we also have A bar. This is my background cosmological model. Let me now consider another cosmological model where rho is equal to rho bar into 1 plus epsilon, slightly different cosmological model. So A bar will be also slightly different. Let us say it is A will be slightly different, A bar 1 plus delta. Okay. Now we would like rho bar A bar cube to be the same as rho A cube. Okay. So what we see is then this gives us a relation we will assume that epsilon and delta are extremely small. So this is going to be 1 plus epsilon plus 3 delta. Okay, which essentially tells us that delta is equal to minus 1/3 epsilon. Okay. So if I have another cosmological model which is slightly disturbed, and then the disturbance in A and disturbance in rho are related like this. Okay. Now both this and this, they both satisfy the same background cosmological model equations. Okay. So both of them satisfy this. So rho bar, sorry, A bar double dot is equal to minus 4/3 pi g rho bar A bar. Okay. And the perturbed one also satisfies the slightly disturbed one cosmological slightly different cosmological model, which is an overdense region in this background cosmological model, also satisfies the same equation. That also is a cosmological model. So what we have is d square dt square A bar 1 plus delta is equal to minus 4/3 pi g. Then I have rho bar 1 plus epsilon A bar 1 plus delta. Right. So the slightly different cosmological model will have rho A here. So A is, we have seen 1 plus delta, A bar into 1 plus delta. It will have rho here. So rho is rho bar 1 plus epsilon, and it will have A here again. So A bar is A bar into 1 plus delta. So I have written down the same Friedmann equation for the slightly different cosmological model. Okay. now we can expand this. So let us expand it. I will have 3 terms when I do this. The first term is going to be a double dot, a bar double dot into 1 plus delta. Second term is going to be 2 a bar dot delta dot. The third term is going to be plus a bar delta double dot. This is equal to let us get rid of this epsilon. So this epsilon we have seen is minus 3 delta. Epsilon is minus 3 delta. So let us get rid of this. So this will become minus 3, this will become minus 3 delta. So I have 4/3 pi g rho bar a bar rho bar a bar, and then I will have 1, I have minus 3 delta plus delta, so this will become 1 minus 2 delta to linear order, right, minus 3 delta and this is plus delta, the delta square term will be gone. So to linear order, assuming that the differences are small between these two cosmological models, we can write it like this. Now let us look at this first term. The first term is a double dot into 1. A bar double dot is exactly equal to minus 4/3 pi g rho bar a. So this one term will be gone. Okay, so this one term is gone. So the term that we are left with is minus 4/3 pi. Okay, what's the term that we are left with? Let us write it down. So minus 4/3. Okay, let me not. This will be minus 4/3 pi g rho bar a bar, all the factors over here into delta, and we have a term minus 2 delta over here. So if I take this onto the right hand side, this will become minus 3 delta, and this minus 3 will cancel out with this. Okay, so if I bring this onto the right hand side, what I will get, and there should have been a minus sign here to start with. So what I will get on the right hand side is 4 pi g rho bar a bar delta. That's the right. I have taken this onto the right hand side. Okay, so that is taken care of this term. Now I have, then what I have left is a bar delta double dot plus 2 a bar dot into delta dot. So we see that we are led to an equation delta double dot plus 2 a bar dot by a bar delta dot is equal to 4 pi g rho bar delta. Okay, a bar refers to the background cosmological model. This we see is exactly the same equation as this. Right, this is exactly the same equation as this. So what we have seen is that if I have one cosmological model A bar, which is the background cosmological, so let me take a cosmological model A, and I have a slightly different cosmological model solution. This is one solution to the cosmological equations. This is a slightly different solution to the cosmological equations. The difference between these two solutions divided by the background solution gives me the same, gives me a solution to this equation. Okay, so let me explain this to you once more. So what I have shown here is essentially this. If I have one back solution, so this is my equation, A double dot is equal to minus 4/3 pi g rho A. That is my equation governing the background cosmological model. I have one solution A1. I have another solution A1 plus delta A. This is a solution. I have two slightly different solutions. Then this delta A by A1, this is going to give me a solution to the differential equation which I wish to solve, this. Okay. So, this is going to be equal to D with some factor, maybe constant factor. Multiplying or dividing this D with a constant factor does not change it, because it still be a solution to this equation. Okay. So, this is the basic result which I wanted to show you. In the next lecture, I am going to show you, work out explicitly how you can use this to get solutions to the perturbation equation in some arbitrary cosmological model.